So I want to go through these homework questions with you. If you get the answers right, obviously mark them, give yourself the points and move on. Anything you've got wrong, just make sure you fully listen and understand where it is that you've gone wrong so you can make really good, accurate corrections. Okay, here we go. So the first question is obviously a carbonyl question, and hopefully you can see that straight away from the use of the 2,4-DMPH. So read the information carefully. It tells us there's carbon, hydrogen and oxygen only in the compound, but here, easy to miss, it contains 4 carbon atoms, and the fact that we know it reacts with 2,4-DMPH tells us it has to be an aldehyde or a ketone. So when you react the compound with 2,4-DMPH, our observation is either an orange precipitate or a yellow precipitate, and that tells us that a carbonyl functional group is present. So bearing in mind that we have to have aldehyde or ketone compounds here, our possible structures, there are only actually 3, and so we've got a straight chain aldehyde, butanol, straight chain ketone, butanone, or a branched aldehyde, methylpropanol. And the way that you represent those in the answer can either be a structural formula like these or displayed formulae like these. You might find it easier to try the displayed formula to give you that real sense of them being different from each other. So, in this part of the question we have to reduce compound E to compound F. I suspect that this question had another section to it that's been taken out. It's quite an old question from 2000, and I suspect in this missing part of the question we would have got a little bit of an extra clue as to which of these structures compound E is supposed to be, which would make this part of the question more specific. However, we've missed that bit out. These 2 marks are a bit of a mystery. We haven't got them on our version of this, so we're going to assume it could still be either of the 3 possible structures. Either way, if we want to reduce compound E to compound F, we're going to use NaBH4, and in our equation we wouldn't use NaBH4, we'd use H in square brackets as it's suggested here. I've got the molecular formula, so we're not specifying which E structure we're using, but remember always that 2 atoms of our reducing agent, 2 H's, are needed to reduce every single one carbonyl compound in our reactant, and that will give us an OH group, be it primary or secondary, depending on whether compound E is an aldehyde or a ketone. So we're going to allow you then here butan 1-ol, butan 2-ol, or methylpropan 1-ol. And I just realised that we didn't have butan 2-ol on there as an option, so there it is. Okay, next question is talking now about an amino acid, 2-aminopropanoic acid or alanine, and we start with a definition for a chiral centre, in which we need to mention that the carbon atom has 4 different groups attached. So 4 different groups attached alone would not be enough to score that mark. It must be attached to a carbon atom. So I think a relatively simple question here now to show how the chiral centre allows there to be 2 optical isomers, and I think the easiest way to show that is with a mirror image. And so we need to always show the 3-dimensional representation around that chiral carbon atom. There will always be 4 bonds, it will always be in the tetrahedral arrangement with a bond angle therefore of 109.5 degrees, and if our 2 versions of our amino acid are mirror images, we know we've got the opposite optical isomers or enantiomers. In part B we have to think about the isoelectric point for alanine, and it tells us that the zwitterion predominates between pHs of 2.3 and 9.7, quite a wide range there, but remember that represents the isoelectric point of this amino acid where the zwitterion exists. So anything below that pH, as in this first part here, it's below the isoelectric point, more acidic than the isoelectric point, so the base, the amine group, will become ionised, it will gain a proton. at pH 6 we are within the range of the isoelectric point, so the zwitterion will exist and both the amine group and the acid group are ionised. The hydrogen ion from the acid group has been transferred over to the amine group. So finally we've got above the isoelectric point at pH 10 we're going to have the alkaline reaction with the acid group of the amino acid, and therefore the acid is going to lose a proton and become the COO-, the ethanoate version of this amino acid. So remember, with these diagrams it's not really about whether the pH is acid or alkaline, it's whether it's above, below or within the range of the isoelectric point. In part C we've got a dipeptide, so two amino acids have been joined together. We have to draw a circle around the peptide linkage and we have to find out the formula of amino acid K. Now hopefully you can recognise from this R group here that this part of the dipeptide is the alanine, the 2-amino-propanoic acid. When we split these two amino acids we break the peptide link. Carbonyl group regains its OH part and the amine group regains its hydrogen. So to draw the amino acid from this side of the dipeptide we simply copy out all of this structure, and when we get to here we put the hydrogen back on to regain our amine group. Now when we have two amino acids like these two, K and 2-amino-propanoic acid, there are always two ways to construct a dipeptide. The one above here was showing the 2-amino-propanoic acid on the left hand side with its acid group reacting into the amide link, and amino acid K on the right hand side, the amine group forming part of the peptide link. Instead of that we could swap these two over and have this particular amino acid's amine group forming part of the peptide link and this amino acid's acid group taking part. So we simply switch places for those two amino acids, and if we do that then we end up with this structure. Again, the peptide link is there, the bond between the carbon and the nitrogen including the carbonyl and the hydrogen there. And it looks very similar but it's subtly different. This is amino acid K with the acid part forming part of the peptide link, and this is alanine forming the amine part. This question has a simple empirical formula calculation, so you need to do a little bit of revision from your AS studies to make sure that you use the same method. Each individual percentage composition or mass composition is divided by the relative atomic mass of that particular element. Column for hydrogen, column for carbon, column for hydrogen, column for oxygen, divided by 12, 1 and 16 respectively. Now make sure you put a couple of decimal places into the answers that you get from that, and then to show that the molecular formula is this, with quite high numbers of carbons and hydrogens but with only one oxygen, we divide through these three numbers here by the smallest of the three, which is 0.26. So we divide all three by that, giving us the ratio here that's in the molecular formula given in the question. So that's the question answered. We've then got a diagram of cholesterol. Quite common to see a complicated looking molecule and be asked to look at what functional groups are present. Even if you're not asked to do that, I'm recommending that you do anyway. You always look to see what functional groups you might be dealing with in a particular structure. Now hopefully you can see straight away that this OH group here is an alcohol group. This is not a benzene ring, there's no delocalized ring of electrons. That would have made this a phenol functional group, but it's not. It's a cycloalcohol. Alcohol is sufficient for that. And here, again, it's part of a cyclic compound, but it's still simply an alkene, a C double bond C that we've got there. Continuing on from that last cholesterol question, we've got some suggested reactants and we have to decide what the structure of cholesterol would be if it reacted with those particular reagents. So bromine, I would be looking straight away for an addition reaction, electrophilic addition across that carbon-carbon double bond. So here we can see the two bromines added at either side, and if this had been HBr as a reactant, we'd have had just one bromine here. So that's K. Secondly, we've got ethanoic acid as a reactant, and hopefully if you're focusing on the fact that we've simply got an alcohol group and an alkene group, the ethanoic acid is of course going to react with the alcohol group and form an ester. So we're looking for something with two oxygens, and here it is. The alcohol group has become an ester group, and these two carbon atoms in the ester group come from the ethanoic acid. Hydrogen would saturate the alkene, saturate the double bond, so G is the product of simply saturating the double bond, and of course the alcohol group remains intact. For acidified dichromate ions, hopefully that rings a big bell. It's going to oxidise the alcohol, and in this case it's going to form the ketone group that we see here, the cycloketone group that we see here. So now we've got concentrated sulfuric acid reacting at a high temperature, and hopefully you realise, again, a bit of revision from F322 needed, that will dehydrate the alcohol. Now the fact that we've got these two options that we've got to write about here should give you a clue that there are two products that could be made from this reaction, and that will just depend on where the double bond that's formed by dehydrating an alcohol to form an alkene is placed. Our options are J and M, because in J we've got the alkene on one side of where the OH was, and in M we've got the alkene on the other side. Of course, in both cases we've now got two carbon-carbon double bonds, because we've got the original alkene that was there in cholesterol at the beginning. Okay, in question 4 we've got the electrophilic substitution of methylbenzene with the nitronium ion, and it tells us actually what the electrophile is for this mechanism, which is quite nice, but of course you need to be ready to give that if asked. So in the mechanism, the main things we're looking for here are, first of all, that your curly arrow from your benzene ring starts from either on or within the ring and goes to the nitrogen of the nitronium ion, not the oxygen, but to the nitrogen, because that's where the bond is formed. Now, because the nitronium ion is attaching at position number 4 on the benzene ring, the partially delocalized benzene ring must point in the right direction. This semicircle must not extend too far beyond these two carbon atoms here, or extend not far enough. So I suggest that you draw a line halfway between those two, and it should go beyond that line. We now show the hydrogen atom on the same carbon as the nitronium, and we break the bond between the carbon and the hydrogen, so that curly arrow goes from the bond into the ring. The marks here are first of all for the full structure of the intermediate with the partial delocalization, the positive charge, and the NO2 group attached. And then the second mark is going to be for this curly arrow here. Be picky, make sure you get that exactly right. And then the other product, as well as the nitromethylbenzene, is the hydrogen ion that's been removed by this curly arrow. We very often see a reduction reaction following straight on from a nitration. So it's very common to see these two together as a way of making an aromatic amine. And so you need to learn that the reducing agent is concentrated hydrochloric acid with tin. That's the mixture, but in the equation we represent these reactants as H in square brackets because they are reducing agents, just the same as we represent NaBH4 as H in square brackets for that reduction reaction. Now you may wish to learn by heart that 6 hydrogen atoms are needed to reduce a nitro group to an amine group. However, there is a way to remember it. So if you look at the starting point, and we know that we've got phenylamine or methylphenylamine as our product, you can see that from up here. Hopefully you can see straight away that we've got to get rid of 2 oxygens from our nitro group, and that will give you that clue and that link in your memory that you're going to form 2 water molecules. Now once you get that far, you can hopefully then balance the hydrogens in the conventional way. On the right hand side we've got 4 hydrogens from the waters plus 3 in the methyl makes 7, 8, 9, 10, 11, 12, 13. On the left hand side, if we don't count this 6 yet because we haven't put it in effectively, we've got 3 on the methyl, 4, 5, 6, 7, which means we need another 6 hydrogens to make this balanced. And you will find for any nitro group being reduced to an amine group, you will need 6 hydrogens and you will make 2 waters. But if you remember that the 2 oxygens in the nitro group are represented by 2 waters over here, it makes the balancing of the hydrogens easy if you forget how many to write here. On the final page we've got to draw 3 structural isomers of CH3C6H3NO2 twice. So we've effectively got methylbenzene with 2 nitro groups on it. Now I've drawn all 6 possible isomers so that you can hopefully pick out whether or not you've got 3 decent ones. So you've got the 2 nitros together, and that can have the methyl group in 2 different places. We've got the 2 nitro groups separated by 1 carbon, and the methyl can go in 3 positions for that. And then finally we've got the 2 nitro groups opposite each other, and there's really only one place the methyl can be that makes that a different isomer. So any 3 of those is okay for that part. Now we can make lycra from one of those 6 isomers, and hopefully you can see that those 2 nitrogen atoms there must have originally been nitro groups that were then somehow made into amide links, and we can see therefore that this is a position where the 2 nitros would be and the methyl is here. Hopefully you'll find that fairly straightforward. And that's everything. So you can add up your marks now, being careful not to include those 2 marks on the first page that weren't on the version we've used.